In this video, we're going to discuss a new type of function, the rational function. The most basic rational functions come from the reciprocal parent function. This was a special parent function that had a hole in its domain, which resulted in a graph that was broken into two mirror image pieces, one on either side of the y-axis, one above and one below the x-axis. Because there is a break in the domain and a discontinuity in the graph, a rational function is not polynomial as we defined this term. Remember, polynomial graphs must be continuous. Instead, rational functions form an entire new category of functions. These special features, these breaks in the graph, result from the fact that, as its name implies, a rational function is written as a ratio. Specifically, a rational function is a function of the form f of x is equal to p of x divided by q of x, where p of x and q of x are polynomials and q of x is not equal to 0. Since a rational function has a denominator, we have to look for exclusions from its domain, namely anything that would make q of x equal to 0. We recognize that we can't divide by 0, so we ask ourselves, what value or values of x would make us divide by 0? This is where we're going to start our study of rational functions by determining and describing their domains. So let's look at an example. Finding the domain of a rational function is, believe it or not, actually not new for us. We've looked at domains in many different forms prior to this point, but it's worth revisiting because now we're going to extend this idea and talk about what happens at those points in the domain where we have a break. So our first function is f of x is equal to 1 over x. You may recognize this as the reciprocal parent function. So I want to determine what value makes this function undefined. In other words, what value makes my denominator 0? Well, the denominator is just x, so to determine what makes my denominator 0, I just set my denominator equal to 0. Algebraically, we don't have to do anything. It's already solved. So x equals 0 is the value of the variable that would make our denominator 0. In other words, it's the value that has to be excluded from the domain. So our domain is all real numbers except any number that makes our denominator 0. So in this case, our domain is everything except 0. So everything less than 0, everything from negative infinity to 0, and everything greater than 0, everything from 0 to infinity. So we split all real numbers up into two intervals around this individual point that has to be excluded. Let's look at another one. So our next function is f of x is equal to 5x squared divided by 2x squared plus 5x minus 12. So we want to know what makes this denominator 0. So we set our denominator equal to 0, and our goal is to solve for x. Now keep in mind, we do have some stuff going on in the numerator, but it does not matter if the numerator is 0. If the numerator is 0, the whole expression is 0, which essentially means it is defined. All we care about is what makes the expression undefined. In other words, what makes the denominator 0. So don't worry about the numerator at this point. So this particular expression, this particular quadratic, actually factors. If the factoring is a challenge for you, just use the quadratic formula to solve this equation. So it factors as 2x minus 3 times x plus 4. And if we set each of these factors equal to 0, we get x equals 3 halves and x equals negative 4. So if you imagine graphing these numbers on a number line, of course negative 4 comes before 3 halves, but these are two excluded values. So we can have anything that's less than negative 4, we can have anything between negative 4 and 3 halves, and then we can have anything greater than 3 halves. We just can't include these specific numbers in the domain. So this domain is actually going to be split up into 3 intervals around these two exclusions. So we have everything from negative infinity to negative 4, everything from negative 4 to 3 halves, and then everything from 3 halves to infinity. And of course, we use parentheses around each of our endpoints to show that those particular endpoints are not included as part of the domain. They're just imaginary endpoints. Now let's try one more. So f of x is equal to x plus 3 over x squared plus 4. And we want to determine what makes this denominator 0. So we set the denominator equal to 0 and solve for x. So here we don't have to factor necessarily. As long as there's only one instance of the variable, you can just move things around algebraically and then solve for x. So we can subtract 4 from both sides and we get x squared is equal to negative 4. Now I need to get rid of my exponent, so I need to take the square root. And remember, if we're taking a square root in an equation, we have to put a plus or minus on the other side of the equation. So I'm left with x is equal to plus or minus the square root of -4. I simplify this down. I can take the square root of the negative and the square root of the 4 separately. So this simplifies to positive or negative 2i. Well, as we've discussed before in the context of complex numbers, whenever we have something with an I in it, these numbers don't exist anywhere on our coordinate plane. Complex numbers are outside of the scheme of real numbers. So in terms of anything that we would exclude that's somewhere on our coordinate plane, these particular exclusions don't apply for us. So what that means for our purposes is that there aren't any exclusions from the domain. The domain is all real numbers. The only things that would make this denominator 0 are outside of our coordinate plane, so that means we don't have to exclude anything. So next thing we want to talk about is what's actually happening at this break in the domain. The breaks in the domains correspond to very specific things on these graphs for rational functions. So that's the next thing we want to look at. Let's define the term vertical asymptote. So an asymptote specifically is an imaginary boundary somewhere on a graph. So our graph gets really, really close to this boundary, but it never touches it or crosses it. So an asymptote is always going to be a line. It's usually a vertical line or a horizontal line, and our graph can get infinitely close to this line, but it can never cross it. So essentially, it's something our graph approaches. It gives us sort of a shape for our graph, but it's just this imaginary boundary. We can have things on either side of this line. We just can't have anything that touches or crosses this line. So of course, a vertical asymptote is going to be a vertical boundary somewhere on our graph. And it just so happens that vertical asymptotes occur at values of x that make the denominator equal to 0. So in other words, those spots in the domain where we have something that's undefined, something that's excluded, what we actually have is we have a vertical asymptote. Whenever we have a rational function and there's an exclusion from the domain, there's actually this imaginary boundary that occurs at that particular excluded value, and our graph can go on either side of this line. It just can't touch or cross this line. So we saw this with the reciprocal parent function. We had a vertical asymptote on the y-axis. So we had graph on the left side, we had graph on the right side, but we couldn't touch or we couldn't cross the y-axis. So that represented a vertical asymptote for us. There is one exception to this rule, and it occurs when the numerator and denominator have a common factor. In other words, if we were to factor our numerator, factor our denominator, remember they're just polynomials, if there's some common factor we can cancel in the numerator and denominator, that actually corresponds to an actual hole in the graph, not a vertical asymptote. So in other words, if we were to graph it, it's not going to be an imaginary boundary. It's literally going to be an open hole, an open circle in the graph. So we have graph on either side, and then we have a little hole right there in the middle of the graph. This situation is very rare, but you should just be aware of it. If there is a common factor, it should be divided out, and whatever that common factor was that would make the denominator 0, that gives us a hole in the graph. Now, one thing we really have to pay attention to is the fact that a graph cannot cross a vertical asymptote. So whenever we're graphing a rational function, we start by graphing all the asymptotes. Anytime we graph a vertical asymptote, we know that we're going to have graph on either side, but these individual pieces of the graph are completely separate. They're never going to touch, and they're never going to cross that asymptote. Now I need to keep in mind that when we're solving for a vertical asymptote, an asymptote is an actual line. So the form of a vertical asymptote is going to be x equals a number. It's a vertical line, so it's of the form x equals a number. So this is like when we were finding the axis of symmetry for our quadratic functions back a few sections ago. So because it's a line, lines are represented by equations. It's a vertical line, so it's an equation of the form x equals a number. So the number is going to be whatever that exclusion was from the domain, whatever made the denominator 0. But when we actually want to represent the asymptote itself, it's always going to be an equation of the form x is equal to that particular number. So let's try a few examples where we identify vertical asymptotes for our functions. So remember, this is basically just finding the domain, except we're interpreting our answer in a different way now. Wherever there was an exclusion from the domain, that's where we now know we have that one of those imaginary vertical lines, that boundary that we can't cross. So our first function is f of x is equal to 2 divided by x minus 3. So I want to know what makes my denominator 0. So I set my denominator equal to 0 and I solve. So my vertical asymptote for this function is x is equal to 3. So that means if I were to graph this function, I have an imaginary vertical line at x equals 3 across which I can't go. So I have graph to the left, I have graph to the right, but we're never going to touch this line, we're never going to cross this line. This is a complete boundary in my graph that I don't touch or cross. Let's try another one. So f of x is equal to x minus 4 divided by 3x squared plus 5x minus 2. So same procedure. I want to know what makes this denominator 0. So set it equal to 0 and solve. This one factors, but if you don't want to spend the time trying to factor, of course you can use the quadratic formula. It factors as 3x minus 1 times x plus 2. So if I were to set each of these factors equal to 0, I get positive 1/3 and negative 2. So my vertical asymptotes, notice I have 2 in this case, are x is equal to 1/3 and x is equal to negative 2. So in this case, I have 2 breaks in my domain. I have 2 imaginary boundaries, which means that if I were to graph this function is actually going to have 3 separate pieces. So we have graph to the left of negative 2, we have graph between negative 2 and 1/3, and then we have graph to the right of 1/3. But we have these 2 imaginary boundaries that we never touch and we never cross. Let's try one more. So f of x is equal to 4x squared divided by x squared plus 4. This denominator should look familiar. It's the same denominator we looked at when we were looking for domain. So I set my denominator equal to 0 procedurally and I try to solve. As we saw when we looked at this for domain, there are no real number solutions. We can solve this as long as we're willing to introduce complex numbers, but in terms of finding any values of x that are real numbers that exist somewhere on our coordinate plane, we don't actually have any numbers of that form that solve this equation. So because there are no real solutions to this particular equation, that means there are no vertical asymptotes for this particular graph. So when we graph it, there aren't going to be any vertical boundaries which we can't pass. Many graphs of rational functions also have horizontal asymptotes. So these are going to be imaginary horizontal boundaries that we can't touch or cross. So that means if we have one, our graph is going to stay either entirely above or entirely below this particular asymptote, and it's going to inform the shape of our graph. Our graph is going to follow the asymptote as it goes towards positive or negative infinity. So because horizontal asymptotes don't have anything to do with domain the way a vertical asymptote does, we have a different rule for determining whether or not we have one and how we find one. So we're going to compare our numerator, which is a polynomial, with our denominator, which is another polynomial. Specifically, we're going to compare the degrees of the numerator and denominator. So n versus m. Again, when we have a real problem, these are going to be actual numbers. So we're comparing the highest exponent in the numerator with the highest exponent in the denominator. So we have 3 possible cases for how these two numbers compare, and under each one of these cases we have a different situation involving whether or not we have a horizontal asymptote and what it is, assuming we have one. So the first possibility is that n is greater than m. In that case, we do not have a horizontal asymptote. Another possibility is that n is less than m. In this case, we do have a horizontal asymptote, and it's always going to be at y equals 0, which is the x-axis. And our last case is if the degrees are the same, so the same degree in the numerator as in the denominator, then we have a horizontal asymptote, and it's specifically going to be the line y equals a sub n over b sub n, which if you notice comparing our numerator and denominator, those are the leading coefficients for our particular polynomials. So it's y is equal to the ratio of the leading coefficients. Now notice this is just going to be a number, but it's just going to be a number that's written as a rational expression. So y is equal to this ratio of two numbers. Now the biggest difference between a horizontal asymptote and a vertical asymptote is that a graph can cross a horizontal asymptote. It doesn't always do so, but it is possible that it can. So we need to keep this in mind as we're thinking about how our asymptotes work and how our graph is going to look. So each time we find a horizontal asymptote, we're going to have to determine whether or not it actually crosses that particular asymptote, whether our graph crosses the asymptote. So we'll talk more about that when we're looking at some specific examples, but just keep in mind, vertical asymptotes we never cross, horizontal asymptotes we might cross. Now there's one other possibility, and it's much rarer, but it's still something we need to consider. It's also possible that we could have a slanted asymptote. So a slanted asymptote is going to be a diagonal line. We only have this in one very special case. So again, think scenario for our horizontal asymptote. We're comparing our numerator and denominator, comparing the exponents. So a graph has a slanted asymptote if n, the degree in our numerator, is exactly one more than m. So in other words, say n was 2 and m was 1, or n was 3 and m was 2. In those specific cases, we have a slanted asymptote. Now keep in mind, in terms of finding a horizontal asymptote, we would fall under our first case in that situation. So we wouldn't have a horizontal asymptote. But under this special subcase, if n is exactly one more than m, rather than having a horizontal asymptote, we actually have a slanted or a diagonal asymptote. So slanted asymptotes are determined by treating the rational function as a division problem. So a numerator divided by a denominator is actually just division. Fractions mean the same thing as division. So we find our asymptote by dividing, and the slanted asymptote is going to be y is equal to the quotient, disregarding the remainder. So we divide our denominator into our numerator, we take our quotient, and y equals the quotient is going to be our slanted asymptote equation. We will have a remainder. Keep in mind, there will always be a remainder, but you can throw it away. It doesn't actually give you any information about the asymptote. Just like a horizontal asymptote, a graph can cross a slanted asymptote, but it rarely does. So for our purposes, if we have a slanted asymptote, we're not going to worry about whether the graph crosses. Keep in mind it's possible, but it's extremely rare that that's going to happen, only in very special cases. So we're not going to worry about that too much. Our goal is really just to be able to determine these asymptotes, and then for a horizontal asymptote, we need to determine whether or not the graph crosses it. So let's try a few examples where we identify horizontal and slanted asymptotes. And if we have a horizontal asymptote, we want to determine whether or not our graph is going to cross it, and if it does, where is it going to cross? So our first function is f of x is equal to 8x squared plus 1 divided by x to the fourth plus 1. So to find horizontal asymptotes, we compare the degree in the numerator and the degree in the denominator. So the numerator has a degree of 2, and the denominator has a degree of 4. So in this case, n is less than m, so we specifically have a horizontal asymptote at y equals 0, which is the x-axis. So now we want to decide, does the graph cross the asymptote? In other words, do they have a point in common? The way we determine this is by setting our function equal to whatever the value is for the horizontal asymptote. So if graphs have a point in common, it means they have a common x value and a common y value. So essentially what we're doing is we're writing an equation where we're making an assumption that the y values are the same. Anywhere I see f of x, that means the same thing as y. Well, f of x is equal to this particular rational expression, so that's representative of y for this particular function. Well, on our horizontal asymptote, y is 0. So I'm assuming that these two y values are the same. I'm making that assumption. And then I want to show, based on this assumption I've made, what would x have to be in order to make that true. So that's our general procedure for finding where, if anywhere, our graph is going to cross our asymptote, and then specifically determining what that point is if they do cross. So I have a rational equation. I need to solve a rational equation. So we can think of this two ways. Either you need to get rid of the denominator and move it over to the other side, so you can multiply both sides by the denominator. The only problem with that is if we're moving the denominator over and multiplying, we're multiplying by 0, so it's going to go away. So we need to decide, is that going to be a problem? Well, another way to think about this is think of it as a fraction. We have something divided by something else, and we're saying that this particular ratio is equal to 0. Well, the only way a ratio of two numbers could ever be equal to 0 is if the numerator is 0. We know that if the denominator is 0, it's undefined. We're in an entirely different situation. But if the ratio itself is actually equal to 0, that means the numerator is 0. So essentially what that means is we can basically disregard the denominator. All that matters in this case is the numerator. I want to know what would make the numerator 0. If the numerator is 0, the whole thing is 0. So I'm solving for x in the numerator. Move your 1 over and divide by 8. So we get x squared is equal to negative 1 over 8. Well, if I take the square root, I know I'm taking the square root of a negative, which brings me into the realm of complex numbers and i's and things that aren't anywhere on the coordinate plane. So this particular equation has no real number solutions. And just like with our vertical asymptotes and domain problem, if there are no real solutions, it means there's no solution to this problem. So whatever question we're trying to answer, the answer is essentially no. The question here is, do they have a point in common? So in this case, the answer is no. There is a horizontal asymptote, but the graph and the asymptote do not cross. The only, quote, point they would cross at is a point that doesn't exist anywhere on the coordinate plane. So we do have a horizontal asymptote, but we're not going to cross it. So that means if we were to graph this particular function, the graph stays either entirely above or entirely below this imaginary horizontal line. Let's try another one. So our next function is f of x is equal to 8x squared plus 9x minus 5 divided by 2x squared plus 1. And we want to determine whether or not there's a horizontal asymptote. If there is, where is it? And then if there is one, where do the graph and the horizontal asymptote cross, if anywhere? So I'm comparing the degree in the numerator, the degree in the denominator. In this case, they're both 2, so the degrees are equal. In this case, there is a horizontal asymptote, and it's going to be y is equal to the ratio of the leading coefficients. In this case, the leading coefficient in the numerator is 8, and the leading coefficient in the denominator is 2. So it's y is equal to 8 over 2, which reduces down to 4. So this is going to be the horizontal line that goes through 4 on the y-axis. So that's our imaginary boundary that gives us our shape for our particular graph. So now we need to decide, do they cross? Does our graph cross our horizontal asymptote? Do they have a point in common? Just like before, I'm assuming the y values are equal, and I'm showing based on this assumption, either there is no x they have in common or there is one specific x they have in common. So I set my function rule equal to the y value for my asymptote. In this case, because I don't have a 0 on the right-hand side, I just have to follow the procedure for solving a rational equation. So I need to multiply both sides by my denominator, move it over to the right-hand side. As soon as I have anything where there's multiplication in parentheses, I know I'm going to have to distribute. So my next step is to distribute the right-hand side. Distribute that 4 to both of the terms. So your new coefficients on the right should be 8 and 4. Now I want to combine all my like terms. So notice I have two 8x squareds in common, one on each side of the equation. So if I were to subtract one of them from either side to move over to the other side, it looks like they're going to cancel. So if I do that, they combine, they cancel, I'm left with my 9x minus 5 is equal to 4. Add my 5 to both sides, I get 9x is equal to 9. Divide by 9, I get x is equal to 1. So because I was able to solve this equation, the x value I just determined is going to be the x value for the point where they cross. So we essentially were answering two questions. The answer to do they cross is yes, because we were able to find an x value that solves this particular equation. And then the point that they have in common is going to have an x value of 1. Well, how do I decide where they cross in terms of y? Well, x is equal to 1, what is y going to be equal to? Well, we know that the horizontal asymptote always has a coordinate of y equals 4. Every single point on that particular line has a y coordinate of 4. So that means in order for this graph and this line to cross, the y coordinate has to be 4. So we solve for the x coordinate, and then the y coordinate is automatically going to be whatever the horizontal asymptote was equal to. In this case, it was 4. So yes, they do cross, and they specifically cross at the point 1, 4. Now this is the only point where they cross. So in terms of the rest of the graph, we're not going to cross this horizontal asymptote at any other point. So at any other point, we're either entirely above or we're entirely below this particular line. Let's try one more. So we haven't seen one with a slanted asymptote. Let's see what that looks like. So our function is f of x is equal to 2x squared minus 5x minus 3 divided by x minus 2. So I'm comparing the degree in the numerator, the degree in the denominator, in case they're respectively 2 and 1. So the degree in the numerator is greater than the degree in the denominator. So we fall under two cases. First case, for a horizontal asymptote, if n is greater than m, that means we have no horizontal asymptote. There is none. In this case, there is none. There's a special subcase, however. So if n is exactly 1 more than m, which is true for this case, that means we have a slanted asymptote specifically. So there's no horizontal asymptote, but instead we actually have a diagonal line that gives us an asymptote for our graph. So to determine what this line is, what this diagonal line is, we treat our rational function as a division problem. So we're dividing the denominator into the numerator. Let's do this using long division. Now, of course, because of what we're dividing in, we could do this with synthetic division, but as a rule, synthetic division only works in very special cases. So to get the practice, let's do it with long division. You can always use long division. So our first part we're dividing is 2x squared divided by x. Well, this is going to give us 2x, so that's the first part of our quotient. We multiply by the divisor out front, and then we subtract all of that. So the 2x squareds are going to cancel. Then we have negative 5x minus a negative 4x. So that's going to convert into addition. So negative 5x plus a positive 4x is going to give us negative x. And then we bring down our negative 3. Now, negative x divided by x is going to give us negative 1. So that's going to be the next part of our quotient. We multiply and subtract. The negative x's cancel. And then we have a negative 3 minus a positive 2. So that's going to leave us with a remainder of negative 5. So for our slanted asymptote, we disregard the remainder, and then the equation of our diagonal line is going to be y is equal to whatever the quotient is. So in this case, the quotient is 2x minus 1. Our slanted asymptote is going to be y is equal to 2x minus 1. So we've determined all the different cases for rational functions where we have imaginary boundaries we can't cross. We know we can have vertical, horizontal, or diagonal boundaries that give our graph shape and that prevent us from crossing over certain areas. So the only thing left is to put it all together and generate a graph from all these different components. So remember, our function is of the form p of x divided by q of x. So one polynomial divided by another polynomial. Each of these polynomials play key roles in how we generate the graph. So the first thing we want to do, typically the easiest, the fastest thing to find, is to find the y-intercept, which we can find for any function. It's always found by evaluating f of 0. So if we let x be 0, we want to determine what's the y value that goes with an x value of 0. So first thing, find your y-intercept. Next step, determine the x-intercepts. So as always, we set our function equal to 0 and solve. So now we're saying this ratio of two numbers or two rational expressions, or excuse me, two polynomial expressions is equal to 0. Well, the only way this ratio can be equal to 0 is if the numerator is equal to 0. So in order to solve the general form of our x-intercept equation, for a rational function, that's really the same thing as solving p of x is equal to 0. In other words, we set the numerator equal to 0. Whatever makes the numerator equal to 0 corresponds to an x-intercept on the graph. And of course, once we have that individual polynomial equal to 0, maybe we can factor, maybe we can use the quadratic formula, or worst case, everything we did in order to determine the zeros of a polynomial function, we can use for this little individual piece in our graphing problem. Our next step is to identify any vertical asymptotes, anything that makes the denominator 0. We're going to graph these as dotted lines. Remember, they're imaginary. They're not actually part of the graph. They're imaginary boundaries that we don't cross. We have something to the left, something to the right. We don't touch them, we don't cross them. So we graph them as dotted lines. Then we want to identify any horizontal or slanted asymptotes, and we're also going to graph them as dotted lines. And if the graph has a horizontal asymptote, we want to determine if and where, assuming they do, if and where they cross, if there is a point where that occurs. And then our final step, we want to plot one additional point in each of the intervals defined by the x-intercepts, vertical asymptotes, and other points where the graph crosses a horizontal asymptote. In other words, any place where the function could jump from being positive to negative. Now, once we start to put all these components together, it's going to make a little more sense what this looks like, where we actually need additional points. The easiest thing to keep in mind is think about what the reciprocal parent function looks like. We have mirror image pieces, they're diagonal from each other. So we have to have a piece to the left of our vertical asymptote, we have to have a piece to the right. Sometimes we only, once we do steps 1 through 4, we only determine where certain pieces of our graph are. So any sections where it's unclear where the graph would be located, we need to plot a couple extra points to determine where the graph is going to be located in those particular sections, but we'll get there. So once we've got all these components, we sketch our graph. Now this is going to be another great time to use your graphing calculator. Your graphing calculator will give you a very good graph of a rational function. You need to keep in mind it's not necessarily going to show you your vertical or your horizontal asymptotes. All it's going to show you is the branches of the graph. But you can find these things pretty easily by looking at the table function in your graphing calculator. So particularly for your vertical asymptotes, whenever you go into your table function and something is expressed as being undefined, in other words, there's no point there, that's where you have one of your vertical asymptotes. So spend some time using your graphing calculator on this. Make sure, of course, you can determine things and graph them by hand, but you may want to use your graphing calculator just to check your work, get a little bit better picture. So we're going to spend the remainder of the video just looking at individual examples and sketching a few graphs for a few different rational functions. So our first function is f of x is equal to x plus 4 divided by x minus 2. This is the function we want to graph. So first thing we want to do is find our y-intercept if there is one. So this is found by plugging in a 0 in place of x, so evaluating f of 0. So I plug in a 0 to each of my x's, one in the numerator, one in the denominator. This simplifies down to negative 2. So my y-intercept is going to be the point 0, negative 2. Let's do the same thing for the x-intercepts. Again, we only have one y-intercept, but we could have more than one x-intercept. So I want to solve f of x is equal to 0, but the only way that's true is if the numerator is equal to 0. So I can just set the numerator equal to 0 and solve. This is true if x is equal to negative 4. So my x-intercept is going to be negative 4, 0. In this case, I only have one intercept. Next, I want to solve for any vertical asymptotes, so anything that makes the denominator 0. If the denominator is 0, it's undefined, which means there's that hole in the domain, which we now know actually is represented by an imaginary vertical boundary. So set my denominator equal to 0. So my vertical asymptote is going to be the line, the equation of the line, x equals 2. So notice when we solved for our x-intercepts and our vertical asymptotes, we're essentially solving the same kind of equation, but how we write our answer is totally different. X-intercepts are going to be individual points on the coordinate plane, so they're going to be represented by a coordinate pair. Vertical asymptotes are equations of lines. So if we want to write an equation of a line, of course, it has to be an equation. So it's always going to be x equals in this case. So make sure you pay good attention to the way you write specific answers. Form matters a lot in this particular case. Now we need to determine if there are any horizontal or slanted asymptotes. So we compare the numerator's degree and the denominator's degree. In this case, they're both 1. They're equal. So we have a horizontal asymptote at y equals the ratio of the leading coefficients. Well, the leading coefficients are both 1, so 1 over 1 gives us 1. So we have a horizontal asymptote at the line y equals 1. Do they cross? Well, I take my function, I set it equal to the value for my horizontal asymptote, and I try to solve for x. So multiply both sides by the denominator and move it over. I need to combine like terms, get everything with an x on one side, get all my constants on the other side. If I try to move one of the x's over, however, they're going to cancel, and I'm just going to be left with 4 is equal to negative 2. This is a false equation. This is not true ever for any value of x. which means that this graph does not cross with its horizontal asymptote. So when we graph it, everything is either going to stay entirely above or entirely below this particular asymptote. So now we want to just put everything we have together and let's see what other additional points we need. So our y-intercept was -2. Our x-intercept was -4. We have a vertical asymptote at x equals 2. And we have a horizontal asymptote at y equals 1. So this is everything we have so far for our graph. So it looks like we can pretty easily determine what happens to the left of the vertical asymptote. We know we can't cross the vertical asymptote, and we decided that we're not going to cross the horizontal asymptote. So we're going to have just a curved branch on the left-hand side that follows the horizontal and vertical asymptote, essentially in the same shape as what we had for the reciprocal parent function. What we don't know is what happens on the right-hand side of the vertical asymptote. So is our graph going to be above? Is it going to be below? We don't know. We know, however, that regardless, if we find one point that's above, then everything has to be above because we know we don't cross our horizontal asymptote. In the same way, if we find one point and it's below the horizontal asymptote, then the rest of the graph has to be below. So what we need to do is we need to find some point, any point we want, that's to the right side of the vertical asymptote. And wherever that point is, all the other points on that side are going to be. So let's just pick a value. Let's pick x equals 3, something that's close to the asymptote. So we want to determine if x is 3, what does y have to be? In other words, where is the point going to be located? So f of 3 is going to be 3 plus 4 divided by 3 minus 2, which is 7/1, which simplifies to 7. So another point on our graph is 3, 7. So let's add that to the graph. And now, what is our graph going to look like? Let's sum it all up and get a picture. So here's our graph. Here's everything we found. To the left, we have a branch that follows the horizontal asymptote and then slopes down towards -infinity following the vertical asymptote. To the right, because we found a single point and it's above, and we know everything stays either above or below our horizontal asymptote, we have a branch that mirrors the one that we have to the left. So if we put all this together, this is roughly the graph we're going to get. Now this particular graph to the right was generated using a graphing calculator software. So notice the graphing calculator didn't actually include any graphs of the asymptotes. It's understood that they're there, but just keep in mind, depending on what particular software you use to graph your equation, it may not actually draw your asymptotes for you. But algebraically, we know where they are. We determined them already. So this is our particular graph. We have mirror images on either side of these two imaginary lines. Let's try another example. So now we want to sketch the graph of f of x is equal to 4x divided by x squared minus 4. So we start with our intercepts. Our y-intercept is at f of 0. So 4 times 0 divided by 0 squared minus 4. Well, our numerator is going to be 0. Our denominator is -4, which simplifies down to 0. So our y-intercept is the point 0, 0. Now for our x-intercepts, we set our function equal to 0 and solve, which means the same thing as if the the numerator is 0. So if the numerator is 0, the only way that's true is if x itself is 0. So our x-intercept is also going to be 0, 0. Notice that if we have an intercept at the origin, it's considered to be both an x-intercept and a y-intercept. We only have one, which means that for any other point on the graph, it's either entirely above or entirely below any horizontal or vertical asymptotes we have. So this is the only spot where we're ever going to cross one of our axes. Everything else is going to be shaped by the asymptotes. So let's find our vertical asymptote or asymptotes. So we set our denominator equal to 0 and solve. We can move our 4 over, so we have x squared is equal to 4. Take the square root of both sides, keeping in mind when we take the square root, we have to factor in the plus minus. So x could be 2 or x could be -2. So this particular graph is going to have two vertical asymptotes, one at -2 and one at 2. So that means when we graph it, this graph is going to have three pieces, one to the left of -2, one between -2 and 2, and then one to the right of +2. Now let's look for any horizontal or slanted asymptotes. So we compare the degree in the numerator and the degree in the denominator. Numerator degree is 1, denominator degree is 2. So n is less than m, which means we have a horizontal asymptote and it's at the line y equals 0, which is our x-axis. So if we have one of these, we will only have one. This is the single horizontal asymptote. Now we need to figure out, does our graph cross it? So we set our function equal to 0 and solve. We can move our denominator over or just recognize solving this means that 4x has to be 0. It means our numerator has to be 0. Well, this is true if x equals 0, which means these two graphs, the graph and the horizontal asymptote, cross at the point 0, 0. Well, that point should look familiar. That was actually the x-intercept and the y-intercept. If the horizontal asymptote is our x-axis, and we already know that we've crossed the x-axis, then that just so happens that those 2 points coincide at that particular spot. So this specific crossing point is at the origin. So every other point on the graph is entirely above or entirely below this horizontal asymptote. Let's put everything together now. So we found our intercept at 0, 0 at the origin. We have a vertical asymptote at -2 and at +2. And we have a horizontal asymptote at y equals 0, which is the x-axis. So what we don't know is what happens to the left of the vertical asymptote. We don't know what happens on either side of the x-intercept, and we also don't know what happens to the right of the second vertical asymptote. So honestly, we have these boundaries, but we honestly don't know too much about the graph. So we need to plot a point from each of these 4 sections to determine what happens in these particular locations. We know that once we find what happens for one point, because we can't cross our asymptotes except for where we've already noted, that one point is going to tell us what happens for every single other point. And then we're just going to graph it so that our graph follows the shape of the asymptotes. So let's pick x equals -4 for the far left-hand side of our graph. So we plug that into our function, simplify everything down, and then if we reduce our fraction, we get -4/3. So for -4, the y-coordinate is -4/3. So that's going to be located below the horizontal asymptote. So that tells me that to the left of the left-hand vertical asymptote, everything's going to be below the x-axis, below the horizontal asymptote. Now let's see what happens at -1. So this is between the first asymptote and our x and y intercept, which happened to coincide in this case. So f of -1, plug in -1 to your function, simplify everything down, reduce your fraction, and we get 4/3. So when x is -1, y is 4/3, which means at this particular spot we're above the horizontal asymptote. Now let's see what happens at x equals +1. So now it's between the x-intercept and the second, the right-hand vertical asymptote. So f of 1, plug in 1, simplify your fraction, reduce it. When x is 1, we're at -4/3. So now we essentially know what's happening between the two vertical asymptotes. To the left of the intercept, we're above. To the right of the intercept, we're below. And then we're just going to follow the vertical asymptote from there. We only cross the horizontal asymptote at that single point. So everything else to the left is above. Everything else to the right is below. Last but not least, what happens to the right of our second vertical asymptote? So let's pick x equals +4. So plug in your 4. Plug it in, simplify, reduce your fraction, and we get the point 4, 4/3. So add that to the graph. So this means that to the right of the second vertical asymptote, everything is going to be above our x-axis. So let's put that all together. We have our asymptotes. We have 3 of them, 2 vertical asymptotes, 1 horizontal asymptote. We cross our asymptote and it just so happens to coincide with both the x-intercept and the y-intercept. And then we have 4 other key points that are going to give us a general shape for the graph. So if we put all of this together, this is our rational graph. And again, this was graphed using a graphing utility software. So the asymptotes were not plotted, but they're understood to be there. So we've seen so far that even though rational functions have some common characteristics, they can vary in shape pretty widely. So the one situation we haven't seen yet is a slanted asymptote. So let's do an example where we're going to have a slanted asymptote. So we want to graph f of x is equal to 2x squared plus 9x plus 4 divided by x plus 3. So our y-intercept occurs when x is 0. We plug in 0. We end up with 4/3. So our y-intercept is 0, 4/3. For our x-intercept, we set equal to 0 and solve. We set our numerator equal to 0. This factors into 2x plus 1 and x plus 4. Again, if you're not comfortable with the factoring, you can use the quadratic formula. You'll solve and get the same numbers. And we get x is equal to -1/2 and -4. So we have two x-intercepts for this graph, one at -1/2 and one at -4. For our vertical asymptotes, we set our denominator equal to 0 and solve. In this case, we get x equals -3. So we have a single vertical asymptote, and it occurs at x equals -3. Now let's see what happens with our horizontal and/or slanted asymptote. So comparing the degree in the numerator and denominator, we find that the numerator has a degree of 2 and the denominator has a degree of 1. So n is greater than m, which means there's no horizontal asymptote. But we're in that special case where n is equal to m plus 1. The degree of the numerator is exactly 1 more than the degree of the denominator, which means we have a slanted asymptote. So we set up our division problem. The denominator divided into the numerator, the quotient is going to give us our slanted asymptote. So 2x squared divided by x is going to be 2x. That's the first part of our quotient. Multiply and subtract. The 2x squareds are going to cancel. 9x minus 6x gives us 3x, and then bring down our 4. 3x divided by x is going to be 3, so add that onto our quotient. Multiply and subtract. Our 3x's cancel, and then 4 minus 9 is going to be -5. We throw away our remainder, and we keep our quotient. So our slanted asymptote is at y equals 2x plus 3. Now again, we do not have a horizontal asymptote. You're either going to have a horizontal or a slanted, possibly neither, but never both. So in this case, we have a slanted asymptote. So let's put it together. Let's graph everything we have so far and see what we still need. So we have a y-intercept. We have our two x-intercepts. We have a vertical asymptote. We had a single one this time. And then we had a slanted asymptote. So remember, graph this using the slope-intercept form. So you graph your y-intercept and then use the slope to find another point on the line, and then just connect your dots. Your graph doesn't have to be perfect, but you should at least cross the y-axis where you're supposed to. So for our test intervals, let's think about this. Let's just use symmetry instead. We know that we have to have mirror image branches. There's always going to be some sort of symmetry, some sort of mirror imagery whenever we're graphing a rational function. So we know a couple of things. We're not going to cross the slanted asymptote. Again, it's very rare. It can happen, but none of our examples are going to be such that we cross a slanted asymptote. We also know that we can't cross a vertical asymptote. So anytime we're on one side of one of these particular asymptotes, we know we're never going to cross over to the other side. So because we already have points on each side of these particular asymptotes, we have something to the left of our vertical and slanted asymptote, and we have something to the right of the vertical and slanted asymptote. Because of that, it turns out we actually don't need any additional points. We know that the branch on the left is going to mirror the branch on the right. And then we also know that the way asymptotes behave is such that they give you a shape for the graph. So the graph is always going to kind of hug these asymptotes without crossing them. So if we keep all this in mind, it turns out we don't need any additional points. We can't cross these asymptotes, and so we've already got points on either side where we could actually have anything happen. So if we put all this together using a graphing utility, this is our graph. So there's that imaginary vertical line at x equals -3, and there's this slanted asymptote that would be difficult to determine just from the graph, but algebraically, because we have the function, we can determine it, we can graph it, and this is the graph of this particular rational function. In summary, we know that the domain of a rational function has exclusions at any x values that make the denominator 0. And we also know that anything that makes the denominator 0 has a very specific function on our graph. So a rational function is primarily categorized by its asymptotes. These are key features on any rational function's graph, and they give us a lot of information about how our graph is going to be shaped. So vertical asymptotes occur wherever the denominator is 0. And they're always going to be of the form x equals a number. Any vertical line is x equals a number. So whatever numbers make our denominator 0, x equals those numbers are going to give us our vertical asymptotes. We can also have horizontal or slanted asymptotes, and we find these by comparing the degree of the numerator and the degree of the denominator. In other words, the highest exponent on top and the highest exponent on the bottom. So if n is greater than m, we have no horizontal asymptote. But if we're in the special case where the numerator's degree is exactly one more than the denominator's degree, we have a slanted asymptote, and we determine it by treating our function as a division problem and dividing and keeping our quotient. If n is less than m, we have a horizontal asymptote, and it's at y equals 0, which is our x-axis. And then our third case, if n is equal to m, we have a horizontal asymptote at y is equal to the ratio of the leading coefficients. So once our numerator and denominator are expressed in descending order, highest exponent first, we take a ratio of the two coefficients at the front of each of the polynomials. So with a horizontal asymptote, we need to make sure we determine where, if anywhere, our graph crosses this particular asymptote. A graph can never cross a vertical asymptote, but it can potentially cross a horizontal asymptote. We also include x and y intercepts. And then once we've graphed all these components, our asymptotes and our intercepts, we determine any additional points we might need to complete the shape of our graph.